So good evening and welcome to week 7 of the course Earthquake Geology, a tool for seismic hazard assessment problem solving session. So here I am Anjali Dikshit. So in this week assignment, the major topics that I will covering is that the geophysical survey or the field survey that we perform to identify the fault scrap or how much let's start. So the first question that we have is, what would be the suitable surveying instrument to measure accurate height of the fault scrap? So I hope you are aware that what is the fault scrap, because in the last session we have covered it. So we just want to measure what is the displacement has happened along the fault scrap. So the options that we have for this particular question is real time kinematics, post processed kinematics, ground penetrating radar, and total station. So all the three are geophysical method, or the not all the three are geophysical methods. Like out of these four, three are the surveying method and one is the geophysical method. And what are these and how they do, that we'll see now. So let's first start with the real time kinematics. So this is the application of surveying which we use to correct the navigation that we use from the satellite system that we have, that is the GNSS, Global Navigation Satellite System. Now one can ask that we already have a GPS to map the distance or to know the distance, then why there is a need of RTK? See, GPS has the precision of only around like 3 to 4 meters, like it is an error of 3 to 4 meters. But when we are on the field, and especially when we are trying to measure the fault scrap, which has a very small movement, it could be around in the scale of millimeter as well. So in that scenario, the error of in the scale of meters would lead to a different, like to lead to a wrong interpretation. So to avoid this kind of situation, we use the real time kinematics method. So that's why it provides, because it provides the accuracy of centimeter level. Now let's understand what is its working. So I hope it is clear that why do we use it and what is the advantage that we get after using the RTK. Now let's understand the working. So here in this figure you can see that we have two receiver unit. One is the base station and one is the rover, which is a movable receiver. So you can move around it where you want to exactly estimate the displacement. So now what happens, first we install the base station, and the place where we install this base station, we already know the exact displacement. For example, it is installed over here. So at this location I already know the exact value of this place, or what is the displacement or the ground elevation this place has. Now what it does, it records the data from the GNSS satellite, which are here currently 3 are available. So it records the data from all the 3 satellites. Then it already has a value. Suppose from the satellite data it gets the value of this particular location x, and it knows that exact value of this particular location is x dash. So it tried to see the difference between the exact value and the predicted value that it got it from the satellite. So suppose the predicted value is x and the exact value is x dash, and the difference would be, suppose, delta x. So delta x is the correction that needs to be added or subtracted from the satellite value. What it does then, now the rover and the base station are connected, not physically, like through the signals. So that delta x correction that base has calculated, it will transfer to, so this delta x correction, it will transfer to the rover. Now rover applies this delta x correction and then calculate the displacement of this particular location. So this is how it provides the accuracy of centimeter level and the precision. So this is the one method that we have for the surveying. Okay, so this is the surveying method, not the geophysical method. Now the other method that we have, so it's the principle is almost same as that we discuss in the RTK. Here what happens, as its name suggests, it is the post-processed kinematics, and here we were doing the real-time kinematics. So we are in the field and the real-time measurement we are getting with the help of this RTK setup. But in this PPK method, that is a post-process kinematics, what it gives, it provides the GPS correction technology used in surveying that corrects the location data after it is collected and uploaded. So remember, whatever the correction it is doing, it is post field. So after you collected all the data and you upload it, and then with the help of the software, it applies this correction that we were applying over here in the real time manner. The same correction it applies in the post collection of the data. So the mainly it uses, it utilized in drone mapping and the land surveying. Now one can ask that what is the need of this PPK? So major advantage of this PPK that it provides is that unlike the RTK, where the connection between the rover and the base station has to be there because there is a continuous transfer of the correction parameter, here both individually acquire the raw data. So here again we have a base station, and the another unit that we have for like the receiver unit is the drone, because it majorly used in drone. And why it used in drone? Because it covers the large area. It can cover around in kilometers, like 2 to 3 kilometers radius it can cover, because there's no connection. The connection between the base station and the rover is not necessary. So what it does, the base station individually collects the data from the GNSS system. Like in this scenario, you can see that we have two satellites available. So the base station receive the record the data from the satellite. Similarly or separately, the rover station also collects the data from the satellite. Then this both data will be stored and will send to the processing unit, where with the help of utilizing the software, the correction are given to the data. So advantage that this PPK gives, that I have already mentioned, is that while performing, no requirement for a good and stable connection. So this is the major advantage. So whenever you want to cover a larger area, or the area where you find lots of tree and lots of hindrance, in that scenario this PPK is a most reliable method as compared to the RTK, and both the method provides the accuracy of centimeter level scale. So they both are good. It depends upon what data you are trying to, what is your application. So accordingly you can choose that which method you want to apply for surveying in the field. Now the third method that we have is the total station. I think you have also performed this total station, because it is a very classic method of surveying. So what it does, yeah, you must have done. Akshay, have you performed it? Okay, yeah. So so in this method, it's a optical electronic instrument used for surveying. So the instrument that we have, that you can see over here, this is the major instrument. So it is based on the optical or electronic instrument technology. What another extra added feature it has is that it can measure the vertical or the horizontal angles. Apart from that, it also measure the slope distance from the instrument to a particular point where you want to measure the displacement. And the function, so from this we can see that it has a three major functions. First is the angle measurement, and the accuracy of the angle is around 0.5 arc seconds. Up to this level it can measure the angle. Second function it has is distance measurement. So it can measure a distance up to like 1.5 kilometers with the accuracy of 1.5 millimeters. So you can see that the difference between the accuracy level scale. Earlier with the two methods that we have discussed, like RTK and PPK, we have the accuracy level of in centimeter scale. But here what we are getting, the accuracy level of 1.5 millimeters, and apart from the distance it can also measure the coordinate. So this is the three basic surveying methods that we used in the field. Now you must have remembered that we also have the fourth option also. So before answering, I would like to discuss all the options. So far I have discussed real-time kinematics, PPK and total station. Now let's discuss ground penetrating radar. So what this, in short we called it as a GPR. So it is a geophysical method. So unlike the three methods that were the surveying method, it is a geophysical method. So since it is a geophysical method, it utilized to image the subsurface. Okay, and to map the subsurface, what waves it uses the electromagnetic waves that has a frequency band of 10 to 1000 megahertz. And also, since it's a geophysical method, it is a non-intrusive method which we majorly use to investigate the underground utilities. There is another method like seismic method which we use to map the deeper features of the earth, but since it is using very high frequency, due to which the depth of penetration is less, and that's why it majorly used to investigate the underground utilities like underlying cables, underlying pipeline, all these kind of phenomena which lies in the meter scale. So if we would like to understand the working of this GPR, so it's a very simple illustration through which you can understand. So first we have a transmitter. So what this transmitter does, it sends the electromagnetic wave in the subsurface, and this line is the surface line. So it sends the energy or the electromagnetic wave into the subsurface, and on the basis of different properties that subsurface has, we got the reflection, and this reflection data is received in the receiver, and then we process the data using some processing methods or processing steps, and then through the output we got some kind of seismic section through which we can identify that whether there is some anomalous feature present in the subsurface or not, because every material has a different property through which it reflects the wave, and that wave response will help us to detect that element or the material that is present in the subsurface. And the property that majorly affect in this GPR method is the conductivity and the permittivity of the material, because here we are using the electromagnetic field, so that's why this permittivity plays a very important role to the signature that we get on the receiver, and how it is impacting that we'll see in the subsequent slides. So far we have understood all the four options that we were given in this particular question. Now would you attempt to answer this question? So what could be the answer, because here we are accurately identify the fault scrap, so definitely it's a surveying method because it is present on the surface. Okay, so what out of, like, since we have a three surveying method, first is the RTK, second is the PPK, and the third one is the total station. So which method has the highest accuracy? Yeah, I can hear you. I think your voice is breaking. Hello. Are you there? I think. Yeah, yeah. Can you answer it now? PPK. Why PPK? Because here. It could be, yeah, but here we want to accurately map the fault scrap, and we can see the fault scrap, and now we want to calculate it with the highest level of accuracy. So what method do you think will work? Has the highest accuracy? Well, just now we have discussed that real time has the accuracy of centimeter level scale. Okay, this PPK is also have the accuracy of centimeter level, but this total station has the accuracy of in millimeter scale. So what would be the more like good choice for mapping the height of the fault scrap? Now tell me. Yeah, which is providing by this total station method. I hope you understood the logic behind it, like why we are marking the total station. So here we know there's a fault scrap, we don't want to explore it, like if the question is bit different, like you want to identify where's the fault scrap or fault feature is there, then you could have use or choose this option like PPK. But since we know the location, we just want to map the height of the fault scrap, we don't want to identify it or search for it. So that's why we are like how much displacement has happened along that fault scrap. And because there's a very, it's not every time, it's not very like good displacement that we can see, sometimes there's a very less displacement. So always use an instrument that has the like highest accuracy in the field. So that's why the answer would be total station. I hope it's clear. Okay, so moving ahead, we have understood this. I think now the answer of this question you will tell me. I just read out the question. It's not visible. Okay. I think okay, I have to share it again. Now it will be visible. Is it? Okay. So, okay, where was, so the question is, the next question is, what surveying instrument has to use before trenching in an area to identify the subsurface deformation? So what are the keywords over here is that we want to identify the subsurface deformation. So as I have already discussed, now answer me, what would be the answer? Yeah, definitely, yeah, good. So because GPR is the geophysical technique that we use to map the subsurface features. So yeah, definitely the answer would be GPR, because other three are the surveying methods. Yeah. So okay, moving ahead. Now the another question that we have is, materials with high electrical conductivity will dash the depth of the penetration of the electromagnetic waves. So since here we are talking about the electromagnetic waves, so what method it would be? It would be GPR. Now can you guess, like just a rough guess, can you make it? What it could be, like what answer would be the correct one? Yeah, like in a logical sense, definitely it will decrease the depth. Now let's understand like few details, like why it is happening. Okay, so the velocity and the attenuation of the wave emitted via GPR are largely dependent on the conductivity and the dielectric property of the investigated medium. So as I have discussed earlier also, that in GPR mainly two material properties plays a crucial role, that is the conductivity and the dielectric properties. Now due to these properties, what happens? The dispersion phenomena happen. Up now, what is the dispersion? So if you look at this equation, where v is the velocity of the GPR wave, c is the velocity of or speed of light, and here epsilon r is the relative permittivity. So you can see that the velocity is inversely proportional to the permittivity. So as long as you will have the high permittivity, your velocity will decrease, and your velocity will decrease, then the energy of the wave will decrease, and since the depth of penetration will decrease. So this is the physics behind like why it is decreasing. So this is the basic relation. It is very simple, like simplified form of the velocity relation with respect to the material property. And the phenomena of decreasing of velocity with depth is called as the dispersion. Yeah. So this electromagnetic wave that we use in the GPR shows the phenomena of dispersion, and what happens in the dispersion, that velocity decreases with respect to depth. Now why it decrease? It decrease because when you'll go deeper, your energy will decrease, because energy and velocity are directly proportional, and since your energy will decrease, then your depth of penetration will get decreased. So if you have a high permittivity material present in the subsurface, then your depth of penetration will be less as compared to the scenario where you have a less conductive material present in the subsurface. So remember this, okay, it's a very important concept. Shall I repeat it again? Yeah. So what, suppose let me draw it. Wait. Suppose you, sorry, is it fine now? Okay. So suppose you have a two kind of scenario, and one body is there, and in the same scenario there is no body, and this body is conductive. Okay, everything is same. like this is a layer A and it is also similar layer A, the next layer is B, this is also similar layer B. What's the difference in these two scenarios is that here we have a conductive body and here we don't have in this first and let's second here, and in the second scenario we don't have any conductive body. Now if we apply the GPR or we send the electromagnetic wave, suppose this is the transmitter, it sends the electromagnetic waves, some will come here, some will come here, some kind of reflection phenomena will happen, reflection. Now in the first case, the depth of penetration, if I talk about the depth of penetration, would be lesser as compared to the depth of penetration in the scenario 2. Why? Because this electromagnetic wave has a property that, or the simple current has a property that it try to travel through a least resistive path. So does the electromagnetic wave. So once it identifies this is the conductive body, so most of the wave will pass through this conductive body. So the rest of there will be very less waves that will go further deeper. But in this B scenario, since we don't have any conductive body, so the general tendency of the wave would be go deeper unless or until the energy will get diminished completely. Okay. And this is what we call the depth of penetration, like how deeper a wave can go. So in this B scenario, the depth of penetration, if I mark the depth of penetration is D1 and here the D2, so D2 definitely would be greater than D1. And why it is? Because here we don't have any conductive body in this second scenario. Is it clear to you? Okay. So remember this kind of logical question can come in like in any exam. So okay. Now in line with this discussion, there is another question I thought of discussing it along with since we are discussing the GPR concept in more detail. So this is the another question. Now the high frequency of electromagnetic wave in GPR will give dash resolution profile and low frequency will give dash resolution. So now here we have to choose high, low, medium. We have like these three keywords and the combination of these three keywords. So what do you think? Just make a raw guess. Why it is so like no here we like the question is not discussing about anything related to the depth of penetration. First okay, leave this question. First tell me what is the resolution. What do you understand by the resolution term? Here let's say beds. Yeah, so what the beds like? Go on further like what's the resolution? You haven't completed yet. Okay, let me first discuss in resolution. So okay. Resolution means like in a very simple language, this is the smallest object that any instrument can resolve. So this is a very abstract concept. Like resolution means it applies to everywhere. Okay, so the resolution means the smallest size of the object then any or one instrument can identify. Okay, so that is the basic definition of the resolution. Now if we talk about in terms of the subsurface, so let me draw a simple again cross section of the subsurface. So suppose we have one layer like this much thick, we have another layer like this much thick, and below that suppose I have a very thinnest layer, and then again I have a broad layer. Now through the seismic or the GPR method, whatever geophysical method that we have, if we want to map the subsurface, what I want that I can easily see all the layers that are present in the subsurface. But if my now the thickness of this particular layer I am marking with red is very small, okay, and if the what I was saying, so if the resolution of my let's say if the resolution of my instrument that I am using is greater than this thickness, suppose the thickness of this particular layer is 2 meters, okay, and the resolution of my instrument is 3 meter, means this is 3 meter is the minimum thickness that it can resolve. Below that it won't be able to resolve. So what happened, like after the survey, if I am using a instrument that has the resolution of 3 meter, so what the profile I will get as the result of the subsurface, that would be like this. So after the surveying, the image that I'll see on my screen or on my computer after processing the data that I've acquired using that particular instrument would be like this. There would be one layer similar as here. Now this layer will not get resolved, so here I will not get any feature. After that, what I will get, this layer and then this. So now you can tell me that this is not giving me the actual picture of the subsurface because my instrument has the low resolution. High resolution means it works in a reverse way. So yeah, correct. So now let's understand now this phenomenon of resolution in terms of frequency. Okay. Now, so this is a simple wave, that how it travels. So the low frequency means that it has a larger wavelength or longer wavelength, and high frequency means it has a very short wavelength. So the wavelength would be this much, and here the wavelength would be this much, correct? Crust to crust or trough to trough. I think you are not okay. So what resolution is? Resolution, the minimum resolution of any wave is lambda by 4. So suppose my wavelength is 28 meters, okay. So the resolution of that particular wave would be 28 by 4, that would be 7. So 7 meter would be the minimum thickness that the wave, yeah, अभी तो आ रहा होगा ना? Okay, why it is every time getting stopped? Sorry. Today computer is acting very weirdly. Okay, I hope it is visible now. Okay. So what I was saying, that always remember when we talk in terms of the wave, the resolution, the formula to identify the resolution is lambda by 4. So you just first need to calculate the wavelength of the wave and then just divide it by 4. So the value that you will get would be the resolution of that particular wave. So for example, if a wave has a wavelength of 28 meter, so the resolution would be 28 by 4, that is 7 meter. So 7 meter would be the minimum thickness of the bed that wave can resolve, correct? Okay. So now tell me, between low frequency and high frequency, which will have a higher wavelength? No, simply just tell me. See, let's go step by step, don't just jump. First tell me which, like between low frequency and high frequency, which one have a higher wavelength? Correct. And the high frequency one will having the short wavelength or the small wavelength. Okay. Now tell me that which will have the higher resolution, the higher frequency one or the lower frequency one? Take your time. Higher resolution. Correct. So I hope you understood the concept here. Okay. Please always remember that whenever they talk about the resolution, just first try to identify the wavelength, like which has the highest wavelength or the smaller wavelength. Then just do the simple math that lambda by 4 would be the resolution of that wave. Okay. Now so let's what it says, that the target resolution and the wavelength are largely determined by the frequency and the material property, like material permittivity or the property. So since we have already dealt with the frequency, so let's stick to the frequency now. So with respect to frequency, you can calculate the wavelength, and then through wavelength you can comment on the resolution. Okay. Now moving further, let's move to the another question, which is not related to this geophysics or the surveying. Now it's related to the geology. So the question states that two consecutive normal faults dip towards each other will result into the formation of dash and dash, okay, of dash and there is another question start, and will form when dipped away from each other. So it's a little bit complicated question, so let's break it in two parts. So we'll focus first in the first part, that is up to here, like just before the end. So two consecutive normal faults. Now I think you will not get confused with the normal fault or any fault concept. Okay. So and now what it is saying, that they are dipping towards each other. So if I'll try to draw, how I'll draw two normal fault that are dipping towards each other. So that is the first task of this question. So suppose I'll draw a fault line first. So suppose one fault line I am drawing like this. No, here it is saying the normal fault only, na? So while the strike slip will come into this, but there is no option of. No, I said that horst and graben are formed whenever we have a dip slip kind of fault, not the strike slip. I don't remember I discussed it with the strike slip, because it can never be with the strike slip fault. I think the option was there, but the answer was not this. Maybe the keyword was there and I just discussed it, that how the horst graben, like in a very vague form, but here. So okay, let's focus to the first part. So what I am trying to do, I am trying to draw two normal faults that are dipping towards each other. So first I draw one fault plane. So the second fault plane, as per the condition that is given under this question, should be like this, because they should be dipped towards each other. So that is why they can dip towards each other. So that would be the raw framework. Now since it's a normal fault, now I need to draw football and the hanging ball. So it is my normal fault. So first I'll start with this fault. Okay, this one fault. So for this fault, my hanging wall would be like, what would be like in normal fault hanging. So in normal fault, what happens? Hanging wall will go up or down? Acha. Go down. Always remember, in normal fault gravity acts, so hanging wall, which is the upper side of the plane, will go down. So as per, so this would be my football, this would be my hanging wall. Is it correct? I am just considering this fault. So since the hanging wall is going down, so I draw it just below, like little bit in the offset of with respect to the football. So this is my football and this is my hanging wall. And similarly, if I talk about this particular, the second fault plane that I have, again here the hanging wall would come, because this is the upper side. If I will draw the normal, so it would be the upper side. So here my hanging wall is already down, so my football will come up like this. Okay, so what I am getting now here, so this is called the, what it's called is the graben. So host is the upside, but since here you want to consider it till here, like what is forming between these two fault. So this is the graben that is forming. Okay. Now the other way around, I think you can do, it's the just opposite to it. If you will do it, you will get the answer. Now to understand the whole, like if we have a system of normal faults, so how it looks like. So this is the system of normal faults. You can see it is forming in the extensional environment that we have already discussed, that normal fault forms in the extensional environment when we push away or when we do the extension. Okay. So always remember, whenever you try to solve a question related to particular topic, try to remember the related concept or related details to that concept. So whenever you heard a word normal fault, so this things should come automatically into your minds. Like normal fault means there would be an extensional environment, hanging wall would go down because gravity acts over there. So this is the basic terms you should always think about it whenever you heard a name normal fault. Okay. So what we have drawn just now, we draw a two fault plane that is given here like this, which are dipping towards each other. So what we got, the land feature is the graben or the landform here. So we got the graben. Now if they are dipping away from each other like this, and if you do the remaining thing, you will see the host will form in between the fault that are dipping away from each other. Okay. So this is how host and graben formed in the normal fault scenario. So even in the question they can ask that in what kind of fault system you can see the features of host and graben. So you now know the answer, correct? Yeah. Okay, I think I am done from my end. So if you have any query, then ask, and if not, then we can close the session. And yeah. So Akshay, or I hope everything is clear to all. Yeah. This NPTEL exam. I think it's an online exam, right?